Well, thank you for the very kind introduction. It's really an honor to be here and in an institute named for Isaac Newton. A few summers ago, I was in an institute occupied by the chair of Galileo, so I think coming to Europe, I have a chance to visit the roots of mathematical greatness, and it's always a pleasure. It's always a pleasure to be in England. Thank the organizers for inviting me. I want to emphasize the importance of the group of people I've been working with for the last probably 20 years on turbulent questions in fluid dynamics. And this is simply the more recent people, but the full list would be quite a bit longer. I should say that it's not possible to do the work that I'm doing without having a team of people working with me, extremely talented people, very good. Without top people, I think what I'm going to show simply wouldn't have happened. So I boiled down what I'm talking about to, first of all, an introduction, and then because this is a mathematics audience, I'm thinking a little bit like a physicist, but I'm going to do this mathematically to some extent. We have existence and convergence questions, and we have non-uniqueness. Normally you have existence and uniqueness, right? We have existence and non-uniqueness. And that's actually a crisis for people that care about the problems I'm mentioning, which is high Reynolds number turbulence, so that's quite a lot of people. And I propose at least a cure of types, and we'll go through some examples. So for the introduction, to explain the ideas in a simple, non-technical way, what I'm trying to look at is the fluid microstructure. Now, I think that people in this audience understand what microstructure is all about. As far as I can tell by looking at the program, half the people are doing microstructure, so I don't have to maybe belabor that point. What I'm claiming is that it depends on the laws of physics. Hey, everybody knows that here. I don't have to argue with you people. I'm used to an argument, but this is going to be a soft audience, I think. Everyone knows that there's a physics that governs a microstructure. You don't think so? Okay. And it also depends, unfortunately, on the numerical algorithms. So how do we get the answer? We get the answer with numerical algorithms. It's supposed to teach us what the laws of physics are. That's completely backwards. So there's a mathematical challenge, which is the non-uniqueness of solutions. We're typically looking at Euler equations, that is, the transport terms are zero. And therein lies the problem, because the transport, they're negligible at computationally feasible length scales for engineering scale problems. But the transport is actually, governs the microstructure. And the microstructure governs the full solution. So even though the transport is zero, it's terribly important. How can that happen? Well, we'll let away a secret. There's more than one transport coefficient. So you set them all to zero, but the question is the rate. So you've got a lot of 0 over 0 indeterminacies, and therein lies the non-uniqueness. Okay, I just gave away the whole talk. You can now go back to sleep. So reacting flows depend on mixture fractions and temperature at the atomic scale. How does a reaction occur? Two atoms touch each other, and then they interact, and they get you change the molecular state or the atomic state. These are permanently subgrid phenomena. From the point of view of a numerical analyst, you worry about subgrid phenomena. Anything that's atomic has to be subgrid for continuum fluid dynamics. So the mixture and the thermal microstructure governs the reaction rate. Now, if you change the reaction rate, you're going to change the solution big time. You're going to see the difference, like either there's a fire or there's no fire. So it's certainly observable. So the microstructure has observable consequences, even if you can't see the microstructure directly. Now, the existence of solutions, I don't want to downplay this. This is a mathematical issue, but putting on my physicist hat, I would say it's not central. And if you talk to a physicist, they believe that if they have reasonable equations, there must be solutions. You talk to a numerical person, they're computing, they believe they're computing solutions, at least approximations. So from a scientific, not from a mathematical, but a scientific point of view, I would say this is not a central scientific issue, it's a central mathematical issue. Now, to support that, there are weak limits in the form of Young measures. These weak limits, unfortunately, don't satisfy any equations, and so there's some more work to be done, but at least there's the beginning. If you assume Kolmogorov 1941 statistics, no physicist, I believe, would ever question this. This is practically like a gospel, although among physicists. If you believe this, and you look at those equations, you know what? In disguise, they're a Sobolev inequality. A Sobolev inequality is like a jewel when you go to prove an existence theorem. It makes things work. It's the engine, it's the locomotive. So Guichang Chen and myself proved existence for the Euler equations. Now people try their best to prove existence for Navier-Stokes and don't succeed, strong solutions. And this is harder. This is the Euler equation. So the way we succeeded was by adding a hypothesis. So mathematically this is cheating, but physically it's not cheating. It's the true answer. So I think that this settles from the point of view of practical physics the existence theory for turbulent flow. This is for incompressible, and I think it needs extension to compressible, and you have to extend Kolmogorov statistics as an assumption to do that. But the non-uniqueness is fundamental. Now there's a mathematical non-uniqueness, and people have these solutions that are zero, and all of a sudden they erupt and they're non-zero, and then they go back and they're zero again. And I think they're really probably completely pathological and not very physical. That's a personal opinion. They have all the properties, appear to have all the properties people want, so they're having trouble getting rid of them. And I propose one further property. I don't know how to get rid of these solutions, but I believe they don't satisfy Kolmogorov 41. So somebody could look at those non-uniqueness theorems and try and see whether they have fractional derivatives, roughly 1/3 order fractional derivatives. They probably don't. But I'm talking about something quite different. This is physically reasonable non-uniqueness, and it's observed in numerical solutions, and it's understood physically. However, not very well understood because people also like to forget about it. So I think it's worth reminding. The physics basis of non-uniqueness. The compressible Euler equation has three-dimensionless parameters: Reynolds number, the Prandtl number, which is shear viscosity divided by thermal diffusivity, and the ratio of two viscosity shear to bulk. Now you set the Reynolds number to infinity and you have two-dimensionless parameters. So why should you have a unique solution of an equation that has two parameters in it, two-dimensionless parameters? It defies logic. And in fact, it isn't true as far as we can tell. And that's really what I want to talk about. Numerical simulation of turbulent flow. The Reynolds scale is typically not resolved. This is for engineering scale calculations, and it will not be resolved for at least one, maybe 2 decades, even in taking Moore's law and computers into account. So it's effectively infinite. But the other two remain, the ratios remain, and their ratios determine the non-unique microstructure. For the n species Euler equation, there are n-1 Schmidt numbers. These are shear viscosity divided by species diffusivity. So you have plenty of dimensionless parameters, you have plenty of non-uniqueness. So to put this in physical terms, the microstructure says, is that mixture of small regions, each hot and cold, or is the thing uniformly warm? Sometimes you take a shower and the plumbing isn't very good, and somebody uses the cold water upstairs, and all of a sudden the shower is hot. So that's an example of a microstructure when you're taking the shower in the morning. Is the microstructure a mixture of regions, each pure species A or B, or is it uniformly mixed, or somewhere in between? So that's what I mean by microstructure. There's a lot of microstructures. This is rather simple relative to the microstructures people are discussing here, but still important in its own right. So the problem with this now is that numerical algorithms have their own notion of transport. There's numerical viscosity, numerical mass diffusion, etc. And these are no reason to think these have any physics in them, so we add extra terms called subgrid terms, and they represent turbulent viscosity, turbulent mass diffusion, etc. And they describe the effects of all the small scales that you haven't resolved. And there's a systematic theory which I'll describe in summary form, which uses the coefficients for these terms. So this is a solution without parameters in it, and so it's a very excellent starting point. Even so, it might not be correct, and so you might need to do a final adjustment to achieve agreement with experiment. Now, this is bad news for the people that think they're going to solve all the problems in the world with some exascale computer, because when you get through, you still don't know if you're right or not. You still need experiments. So maybe that's not a European disease, but it's certainly an American disease that computers are going to do everything. And there are probably Americans listening, so my apologies. Improved algorithms. So this is an alternate solution, not recommended. We have a problem with the numerics. We get better algorithms. So you get the best momentum solver, and people are very clever. You get the best concentration solver, and people are very clever. It does not solve the problem, because good numerical viscosity divided by good mass diffusion does not equal a good Schmidt number. Why is that? Well, because typically you're much better at viscosity than mass diffusion. And so this number here is just typically out of balance with the viscosity, and you get a bad Schmidt number after all that effort. So the way to improve the algorithms, which nobody wants to do, is degrade the momentum solver so it's equally bad as the mass diffusion solver, and then you're in business. I've never heard anyone do that, but that's the proper way to compute. And that's what these subgrid terms do for you. It's a little bit more respectable intellectually. So I want to say a little bit about existence and convergence questions. Now, I think traditional notions of convergence do not apply because new phenomena arise as the mesh is refined. So pointwise convergence is elusive. Now, the theorem I referred to with Guicheng Chen actually says the opposite. You do get strong convergence, but I think in practical calculations, the mesh is not sent to zero. It's refined by maybe 3 levels if you're lucky, if you have a big budget. And so you're not really doing mesh convergence. You're looking at asymptotics as the mesh is varied by a factor of 3. You probably need a factor of 20 to get full convergence. So 3 is just a drop in the bucket. So you're looking at asymptotic properties. And so you remain in this mode up here, even in spite of that theorem. So we want to fix the observables, which is a function of the solution. The observables has a length scale, typically. And if the length scale is larger than the mesh, there's a chance that it might converge. And so that's one type of convergence. But I'm talking about microstructure, and these are permanently smaller than the mesh. Chemical reactions depending on atomic scale microstructure. Convergence of microstructure, we have to look at stochastic descriptions of convergence.
I mean, the chemical reactions depend on the local structure because they are heavily nonlinear. You cannot average them.
Well, if you average A and B, you get a uniform mixture. But if you're doing chemical reactions, you need to know the concentration of A and the concentration of B, not averaged over some region, but the local concentration. So the chemistry is nonlinear. That answers your question. The chemistry has an A-B term. Concentration A times concentration B. Arrhenius tonics has an exponential in the temperature. So it's definitely nonlinear. Most physical processes are nonlinear, the ones we care about. The other ones are not that they're unimportant, is that they've been solved long ago. So stochastic convergence typically is the mean and the variance. Now, if you have an exponential in the temperature, that won't do it. So we want to get all higher order statistics, that is convergence of the full PDF, or its first integral, the cumulative distribution function CDF. And then you can, with that convergence, you get convergence of nonlinear processes happening on the physics. So that's the relevant convergence that we need. Now, a Young measure, this is the right audience, I think, for a mathematical existence theory. Does everybody know what a Young measure is? No, all right, it's not the right audience. A Young measure is a weak solution of a partial differential equation. And in weak solutions, you have to integrate over test functions. The test functions for a Young measure include not only space and time, but the solution variables themselves. So you integrate over density, pressure, energy, what have you, as well as x, y, z, and t. So it's a probability distribution indexed by space, but it's a probability in the field variables of the solution. And it's sort of an exotic thing that comes up in existence theory, and I kept waiting for it to have a reality in physics, and I think we've discovered that here. So they're not just functions of space-time, but they're actually functions of the solution, the test function, functions of solution state variables. So you get a probability a probability distribution in the state variables at each point in space and time. These things can be differentiated so they can be plugged in the equation. They're either a solution or they're not. So we consider numerical convergence in the sense of Young measures and the associated CDFs. And even if you have convergence in an LP norm, I think this is more realistic in terms of what's actually happening. And so we have an algorithm, which is a post-processing algorithm, so anybody can use it. You bin the solution into supercells, and the set of the solution variables in a supercell, the supercell gives you coarse grid spatial resolution, and inside the supercell you get a lot of solution values, and they're in finite approximation to the measure in that supercell. So it's a little bit like the resolution of the uncertainty principle. In the uncertainty principle, you can know as much as you want about position, but then you know less about the velocity. And this is the same story. You have some trade-off between velocity information, position information. And the supercell is what defines that trade-off. So it's a quite new notion of convergence, but I think it's very suitable for turbulence. So I'm going to give you some examples to let you understand this. We're solving large eddy simulation, Rayleigh-Taylor instability, and we have an 8x2 array of supercells, which looks very coarse. When normally you have 500 cells, 200 cells in each direction. I'm talking about 8x2 cells. Why do I think that's okay? Because the statistics typically are slowly varying. What's rapidly varying are these statistical fluctuations, but the parameters that define the fluctuations are slowly varying. So here is the raw data, and you have 3 levels of mesh refinement. So we have a coarse grid and a fine, medium and a fine grid. The medium and fine, by eye, they look like they might possibly be the same thing. And the coarse is really quite a bit further away, but it has some relation. So how do we formulate that this is actually a convergent process? That's the challenge. Well, here are the PDFs comparing medium grid to fine grid, and you can see that sometimes they're pretty good and sometimes they're sort of so-so. But anyway, that's what they are. So we integrate the PDFs once. That's the first integral, and that defines the CDFs. And of course, when you integrate, things get nicer. And so you get rid of some statistical noise. And these all look about the same, going from here to here, going across. This row looks really pretty nice. The CDFs are where we do our convergence study. And so this is an L1 norm of the differences of the CDFs on an 8x2 grid. And the point is that the medium defined comparison over here has a lot more blue, and a lot less yellow. So you see blue is good and yellow is bad and red is terrible. And so you'll get a lot more blue and less yellow. So it is really a better solution. So that's proof of convergence, and then you can make a norm out of that mosaic, and you can see the norm convergence. So here's the norm of that supercell difference, coarse to fine, and let's look at the L infinity norm. That's the more difficult one. And this is a 9 by 8 by 1 supercell, and it looks like its convergence roughly order 1/2. And then we look at a 36 by 12 by 1 supercell. Its convergence looks like it's order 2. So there's a huge difference in the convergence rates between large supercells and small supercells. So I think the convergence for these small supercells is dominated by statistical errors, and they've been to some extent mitigated or removed here, and you're getting more numerical errors and better convergence. So I think that's an encouraging plot. We need, I think, to refine this. It's sort of an isolated point in a huge sea of problems. So the benefit of all of this is that nonlinear fluctuations converge, and they're captured in the convergence process. True nature turbulent flow. Conjecture, we get CDF convergence with Kolmogorov scaling exponents as long as there's no change in the solution microstructure. So if you believe that you're at a length scale where nothing else is going to happen physically, then you should expect convergence of this type, and you get convergence even to the physical answer, which will resolve the non-uniqueness. So why do I claim that this is actually non-unique? Well, I don't want to embarrass the unfortunate authors of the published papers, but I will at least show some of their results without mentioning their names. And you can see that it's visibly non-unique. And then we did our own study. We modified the code to muck up different kinds of algorithms, and the answer changed. And then we have a theoretical explanation, which I've actually already given you, and its cure, which I've already explained briefly. So this is not unique to the history of applied mathematics. Going back to the 50s or so, or at least in Courant Friedrichs, they explained that flame speed at the Euler level is non-unique, but is cured if you add thermal conductivity. Shock polars have non-unique solutions. They're cured if you give all the initial and boundary conditions. And three-phase flow in oil reservoirs, my colleague Dan Marchison and his team solved those, and they are non-unique solutions of Riemann problems. And they're probably cured with transport phenomena added. They didn't carry out that.
Transport means adding diffusivity.
Well, in a complicated physics problem, there's probably more than one transport. So that's thermal and mass diffusivity and so on. So you have to add the relevant diffusivity. Also, for oil reservoirs, there's a lot of local microstructure in the rock, and so there's heterogeneity in the underlying problem, and that should be added. But I mean, basically, yeah. Basically, the answer is yes. Well, I've already been through this, so I'm going to skip over this. So the cure is you use turbulent transport to set the missing dimensionless parameters. There's a method for setting dimensionless parameters. It's called these are called dynamic subscale terms, and you have to postulate the term. You postulate something sensible, and then it has a coefficient. And the point is, there's a theory to finding the coefficients, and so that gives you a uniquely defined algorithm once you have settled on what coefficients. People usually use this Magarinsky type term. So an example of a subgrid term is the average of the product minus the product of the averages. Everybody knows that's bad news, right? Does everybody know that? And the difference, the error, is the subgrid term. And that is a fluctuating pressure if it's in the pressure equation, or fluctuating velocity or momentum in the fluctuating momentum in the momentum equation. So this Reynolds stress exerts a force. So it's like a turbulent force on a wall, which is different from the static pressure. There's a turbulent pressure also. So the dynamic subgrid models assume, say, for example, a Smagorinsky form, and then you compute the coefficient theoretically. Now the problem is that the numerical truncation error is also a subgrid term. It enters in exactly the same way. So normally for numerical transport is actually too big. So in a sense it's an unsolvable problem because you can always add diffusion, but you can never remove it. Very hard to remove it. So you're sort of stuck with an incorrect answer unless you artificially degrade the rest of your solution to match, which nobody has the courage to do. The cure for the excess numerical transport is the front tracking method, which is the numerical high dimension analog of the random choice method that was mentioned in the introduction. So the full package is front tracking, large eddy simulation, subgrid models. So I think I said already what's in this slide. Now we want to do verification and validation. So verification is the mathematical proof. It's typically things like mesh convergence, and validation is experiment. You have to agree with an experiment. And we're looking at two kinds of fluid mixing, either acceleration driven or shock wave driven. So for the Rayleigh-Taylor, these are the relevant parameters. There's a instability growth rate with a length scale h, and it looks a little bit like Newton's law, except that this alpha here is a drag coefficient. It's not 1/2. And there's a renormalized gravity that has to do with buoyancy. And then to get the microstructure, the experimentalists have not been very cooperative. They do rather simple things, but there are some measurements of the second moment. So this is the second moment of the concentration. Now here is a simulation, and you can see it's beginning to grow, and it'll eventually go through all the data points. Here it is going through all the data points. Okay, so here's the complicated solution. So this justifies a free boundary condition talk. This is my free boundary. And I think you'll believe that that has a statistical aspect to it. So we did a lot of different experiments, and we were perfect in all cases but one. We think we know what's wrong up here, and we're going to fix that. But in any case, we're basically getting zero discrepancy from either simulation uncertainty when we did that, or experimental uncertainty. And we sufficiently accurate, you can tell the difference between one experiment and another because they have different transport coefficients. So the non-uniqueness in the large Reynolds number limit, there's an algorithmic dependence. So people that don't use this algorithm, they compute it anyway, and they differ from experiment by 100%. And compared to each other, they differ from one another by 50%. They claim that this is due to initial conditions. We tested on initial conditions and found initial conditions for the problems we're looking at are 5% effect. So it's not 100%. So this is just definitely a scientific error. So the intrinsic variation within the experiments, this has to do with transport, is around 20%. And well, it's this. We varied the transport. We got a 5% effect. I'm sorry. I don't have it right away what this is due to, but it's not transport. Now here's a slide on numerical algorithms. So the unclosed terms. are typically order delta x squared, delta u squared. Numerical truncation error is delta u, first order. Why do I say first order? That's because everyone has a third, fourth, sixth order algorithm, which is first order near discontinuities. Therefore, it's first order. It's first order where it counts. So in spite of high order, the errors are order delta x. And for large solution gradients, first and second order are easily confused. So the truncation error contributes in the same manner as the closure term, the subgrid terms. And the large Reynolds number limit is sensitive, and so it's sensitive to the algorithm. So we minimize this, and so that's really how we got sort of perfect answers. So here's a slide I want to go over a little bit. It's got quite a few things on it. There's two experiments, so I'll talk about the top experiments. These are the experimental numbers with the error bars. And these two simulations, this is still in progress, and it looks as though it's going to go through this final error bar pretty nicely. These two are our front tracking simulation. And they missed two data points, these data points probably look like they're experimental errors. And then I want to look at a DNS simulation, which is here. Now the DNS simulation misses the error bars for roughly 2/3 of the time period of study. And it misses it by, on the average, about 30%, which in most engineering problems not acceptable. Now, there's no guarantee that the experiments are correct, but what is commonly claimed is that DNS is as good as experiment, and therefore you can believe it absolutely. Now, there's two things wrong with that. First of all, no one believes experiments absolutely. All experiments require confirmation, and the number of confirmations required depends on the subject, and it depends on the consequence of the decision associated with the subject. And secondly, what's more serious is that this is actually near DNS. It doesn't quite resolve the Batchelor scale, which has to do with the mass diffusion, which is what's being plotted here. It comes close to that. But nobody has done a scientific study of what DNS is. So it's a challenge to the audience. Here's my challenge. What is DNS? DNS means you solved all the relevant length scales. So here we know what the relevant length scales are, and there's a Batchelor length scale. It's like Kolmogorov, but it has to do with mass diffusion. So delta x is almost equal to Batchelor, and suppose it was equal to Batchelor. Does that solve it? Well, suppose you were resolving a flame, and you had one mesh block inside the flame. Would anyone believe that you had calculated the flame correctly? Of course not. Suppose you're doing flow around the sphere, and an elementary thing would be to get the drag. And you had one mesh block for the sphere. Would you get the right drag? Of course not. So why is delta x almost equal to the Batchelor scale, almost DNS? But there's two missing pieces, and I challenge the audience for both of them. And one of them is a valid numerical definition of numerical mass diffusion with a length scale. And the other is a valid definition of what is DNS in terms of reasonable accuracy results relative to how far you've refined compared to the length scales, Kolmogorov and Batchelor or whatever, Schmidt, whatever they are. And this is another calculation involving a high Schmidt number, very narrow error bars, and we have to redo this. We ran into trouble at this point. So anyway, those are my challenges to the math community to figure out what DNS really is, because people are using DNS and they're claiming that it's right, and they're claiming that their codes are right because they're getting a DNS to prove it. And I think it's like solving a flame problem with one mesh block inside the flame. And you're going to get some answer, but that doesn't say it's right. So this is the same thing in words. I just went over that, so I don't have to go over that more. So we get pretty good, nearly perfect results for alpha. The mesh effects seem to be about 2%. I didn't show those results. and we get stochastic convergence of the CDFs, validation, comparison to experiments, validation for second moments, probably unique, and it's just the beginning of the stochastic convergence. I think that needs a lot more exploration. Now I'll say a little bit about Rickmeyer-Meshkoff. Maybe I should go over this a little bit quickly. So this is a problem we did a few years back. It's a circular imploding shock wave that goes through an interface. On the way out, it goes through the interface a second time and generates very complicated solutions. So this is a visual proof that we're getting convergence of the PDFs. And now you don't have to there's a calling something proof by visual graphs is an insult, and I'm doing that, but we've also done the quantitative proof, so I can. Here we're doing the same comparison of solutions, but we're showing that the Reynolds number is not a strong variable. So this is the same kind of error analysis in supercells, but it's for the effect of changing the Reynolds number, high to still higher. And the result is just only marginally bigger than the mesh error, so it's just marginally observable. Now here we do our own proof of the effect of change of transport coefficient. So this is diffusion 1/10 of nominal, and it doesn't diffuse as much, you can see that. And here is 10 times nominal, and it's sort of flat. So there's a definite difference in the solution when you change the diffusivity. Turbulent, well, you can call that turbulent diffusivity. Now this is the theorem that I referred to earlier. I think we want to extend this in several directions. I hope maybe that can be a byproduct of this conference. We have interpreted the turbulent modeling in a renormalization group expansion. A renormalization group is a popular method for turbulence, and we're taking a somewhat different point of view than other people. In particular, we had to reformulate the renormalization group itself to make it fit. But in any case, we understand things like the definition of the subgrid terms from the renormalization. Now, here's a simple explanation of where these coefficients come from. So you have the Leonard stress is the difference of subgrid terms at two mesh levels. And remarkably, this subgrid terms, it's called that because it has unobservable terms. The difference, and all the unobservable terms cancel when you subtract at two mesh levels. So these are totally predictive. And then you have the difference in the model at two mesh levels. The coefficient, you assume this is in an asymptotic range, so it has, after scaling, it's constant. You scale this with the correct power of delta x, it's constant. And so you have this equation gives you the coefficient. This is where the coefficient comes from. Very nice theory, due to basically the Stanford group in turbulence modeling. I think I'll skip over this and come to conclusions. Non-uniqueness is understood physically. It's a central scientific difficulty. I think a little bit underappreciated. The bulk flow properties seem to be under good reasonable numerical control. Stochastic convergence and microstructure, I think we have the beginnings, but they're hardly more than beginnings. So, thank you.
Are there any questions?
Yes.
Tried Kelvin-Helmholtz instability?
Did we try Kelvin-Helmholtz instability? Yes, a little bit. We have done rather little, but it should be should follow a very similar pattern to what we've done here. Now, compressible high Mach number Kelvin-Helmholtz has its own aspects to it, but it should fall into the same framework.
So I have a question. So you pass to the limit of high Reynolds numbers in these turbulent flows, and you get non-uniqueness for the Euler system, right?
Do we need what uniqueness?
Yeah.
We don't, well, I'm claiming it's not unique.
Non-unique.
With one exception, which is the incompressible single fluid. As far as we know, that's unique. At least there's no physical obstacle to being unique.
So the non-uniqueness will be for compressible fluids or for two-phase fluids.
That's right.
Okay.
That's right.
And this is something that there are no rigorous proofs of that.
Well, Huichong and I are plotting to have a proof of non-uniqueness. We don't have it yet.
Oh. So,
We'll see. We'll see.
okay. So do we have to give you a time period to announce that?
Probably not by Friday.
Okay. More questions? So the question is, these pathological solutions of the Euler equation
Right.
could be eliminated if they don't pass through the Kolmogorov statistics.
Well, I would certainly eliminate them. I mean, I'll let the authors of these judge for themselves, but most physicists would throw it out.
And what is the answer of mathematicians to your question? Did you pose the question to relevant mathematicians?
No. I don't know how, I would not know how you would establish the property. I would be interesting whether you threw, no matter what you decide to do with the answer, it's still an interesting question. I imagine they would back off. I don't think people like this. I don't think mathematicians like these solutions because they have spent a lot of energy looking for things that might go wrong. They haven't succeeded. But my guess is they've put all that energy because I didn't like them. But that's just a...
Just a comment. I don't know if it's changed, but I think the current record is like 1/5 Holder continuous.
I'm sorry, I'm not hearing you.
Sorry, I believe currently there's 1/5 Holder continuous non-uniqueness, but it's not up to 1/3.
There's a non-uniqueness for what?
Uniqueness for Holder continuous 1/5.
Non-uniqueness for Holder continuous.
But yeah, Holder continuous, but only up to 1/5, not up to 1/3. So it's still below the Kolmogorov.
So that would be non-uniqueness with, this is for incompressible Euler.
Compressible Euler, yeah, like the.
I see. Well, all right. So that's what I get for sticking my neck out and making a conjecture.
But they're still below.
Well, let's talk
they
about
would
it later.
be ruled out by your criterion.
Let's talk about it later.
Any more questions?
We have two comments on your last slide here. First is, why is it running on 15 seconds?
What's that?
Last, your clock here is running on 15 seconds.
Oh, this. Yes.
And then why is it?
This is created by using our front tracking program. That's just a joke at the end.
Okay. If there are no more questions, let's thank our speaker